So, hello, my name is W.Nowakowski, and today I will present you a presentation about quaternionic description of semiconductor quantum dots based electronics, and whole presentation will be based on a paper which is for now on arXiv platform, and I and Mr. Pomorski are the main authors of this paper. So at the beginning, let's figure out what is a quaternion. So the quaternion is a hyper complex number. It contains a real part and an imaginary part. The real part is also known as scalar part, and imaginary part is known as vector part. It's because we think about this imaginary part as three-dimensional space where all of the axes are defined by vectors I, j, and k. The values of these vectors have this property that square of all of them is equal to -1, and multiplication of those values also gives -1, and this three-dimensional space is orthogonal. We can describe quaternions in many forms. One of these forms that we will use in the paper in the future is this presented above. We use the 2x2 matrix with complex values, but also there is around 48 quite similar variants of these 4x4 matrices. We can find out that using Pauli matrices, we can denote this first version of definition of quaternion, and we'll use this description with Pauli matrices in the future in this talk. So our main topic is Hamiltonian position based, and we define this Hamiltonian as it's shown in the equation above. The EP1 and EP2 values are potential energies in two positions, and this terms with TS is Hoping terms. And we find out that with these conditions, that the A in quaternion of this form is equal to 0, B is equal minus P1 or EP2, and D and C are two parts of this Hoping term. We can redescribe this Hamiltonian to the quaternion by multiplying Hamiltonian by 1 over E, or by multiplying quaternion by I. The way that we thought about the way that we were thinking where we created this set of equations was that because we are talking about potential energy, we can always find some point which is in the middle of these two energies, EP1 and EP2. So the distance to this point will be the distance in energy will be some value and negative thing of part of this value. So we will be able to describe this B term with good signs. So when we use this formula and this set of equations, we found out that the quaternion must look like this. But as I mentioned before, we point out that we are using some point where this EP1 and EP2 have the same value but different signs. So we are losing some kind of information. So we create another matrix. We call this matrix A, and it's the average value, arithmetic average of these two energies, EP1 and EP2, on the diagonal part. So we somehow, if we think about this point between this EP1 and EP2 as some kind of normalization factor, so this matrix will have coded in it itself this normalization factor, and due to the fact that this is the same value on the diagonal part, so we can somehow, this normalization, we can put it to the real part of the quaternion in this 2x2 form. So we are doing it by this formula. And if we have a Hamiltonian in some kind of quaternion form, we will right now try to use this quaternion, this Hamiltonian, in some examples. So the first example is an operator of time difference, and the formula to this operator is exponent of the sum over dt1 of the integral of the d tau1 times 1 over IH bar the Hamiltonian. And when we use this formula to this equation, and using Huddersfield-Baker rule, we can find out that this U operator will have the form that is visible on the bottom of the slide of the picture. So with this operator, we can right now try to define something different, something like equations of motions. And when we find out that, when we define that the density operator it is defined that density operator is IH bar times d over dt is equal to Lie bracket of Hamiltonian and density operator. We can, using the formulas from the last slide, we can denote this density matrix using quaternions, and we will obtain the version of this density matrix as it's shown here on the bottom side of the slide. Yeah, so for all of those examples which we show right now are correct if we are talking about some simple example. So one particle that can be in two positions with two energy values. But to describe the more complex sets of particles, we have to define a new function. And this new function, we will call it a generalized double Kronecker sum. Well, we find out that I lost somewhere some word here. So this double Kronecker sum works like this. So we have sum over some index m and n from some values O, P to Rs. And we have Kronecker multiplications of of identity matrices, and all of these identity matrices have the same size as the matrix M, Mn, and Mn, and the value E, the function E that have two variables N and M, is some kind of modificator of the values of these functions. So we can, so I mentioned before, this is the definition, but during the summation, we can find out that there can be some moments where Mn and Mn matrices will have the same index. So there's might be a question what to do in that situation. So this is described here. So during the summation process, this term will look like this. So we will multiply the first matrix that is here by the second matrix. That's it. So the order of writing down these two matrices is quite important. And we've defined in this way this Kronecker sum, we can try to write the Hamiltonian in more complex systems. Right now, we will, in the beginning, we'll try to describe the Hamiltonian of just tight binding model, so weakly interacting bodies. So to describe this this form of this set of particles, we use this double Kronecker sum, where H and M is the Hn is the Hamiltonian of the set of the particle in two possible positions, like it is shown here, and its form is like shown here. And due to the fact that that summing and Kronecker multiplication is adaptable, so we can put the summation of from outside of the Kronecker double sum, and we obtain a term like this. It's quite important because if we want to use the procedure of quaternionizing evolution in time operator, we need to have this summation of diagonal and not diagonal parts of Hamiltonian, which is realized by this part of the equation. So using this formula and the procedure that we use here to quaternionize time evolution operator, we can quaternionize the time evolution of some state function, and the result of the quaternionization procedure is shown here in the bottom of the page. So the next step, when we describe to the set of weakly interacting quantum dots, the next stage is to implement some kind of electrical interaction. So using the double Kronecker sum, we can denote the Hamiltonian of interaction in the following way, where sigma 0, sigma 1, 2, and 3 are Pauli matrices, as it was shown here. And the EC function that is in the generalized double Kronecker sum is correlated to the electrostatic due to the Coulomb force. So it's the E squared, because we assume that the particles have the charge equal to E. And to the electron charge, we are thinking about two interacting electrons. And the function d from AB is the function that describes the distance between some particle A and some particle B. Yeah. So the conclusions are that, as I mentioned before, this is a part of a paper that we written with Dr. K.Pomorski, and the further plans are to use the Quaternionic description to maybe create some kind of calculating system that will maybe be more effective than classical mathematical models that are used in computers to simulate the interaction between quaternions, between particles, or position-based qubits. So yeah, so thank you for your attention.